Hello, my name is Junho Wohn, a graduate student at Hanyang University, and today I'm going to present our paper, Synchronization-aware NAS for efficient collaborative inference on mobile platform. Recently, artificial intelligence and its deep learning model are one of the hottest and fast-growing area in computer science engineering. And after early deep learning models such as AlexNet has been introduced, there have been now many applications like MobileNet V2 that utilize deep learning application in our daily lives. So to bring the deep learning application into a mobile system, we can first consider a cloud approach. However, for the real-time application, the latency is critical and the inference process should be often performed without network connection. Furthermore, there are some privacy issues, especially in the personalized systems, and high data center workload overhead can be also the major issue. Therefore, there are increasing demands for on-device inference, and there are many important attempts on developing specialized hardware for on-device inference. So as you already know, recent mobile devices are generally consist of the multi-GPU and CPUs. However, since most of the existing deep learning models are based on the assumption that only CPU or GPU is utilized to run the deep learning model inference. So therefore, one of the computing resources are not utilized at all. Then how can we fully utilize the all available computing unit? So to increase the total utilization, we found some promising clues in ensemble models, which run multiple models and gather the result, and they both end result to increase the total accuracy. Therefore, from the characteristic of the ensemble model, each model can be assigned to a different computing unit and run concurrently. Then the final output of the model prediction can be aggregated. So though the ensemble methods look great, there's still one remaining question. Why should we only aggregate the last result? Can we aggregate more actively? So therefore, in this work, we first take an ensemble-like approach, which allows each computing unit to handle the individual models, then aggregate their prediction result to perform the collaborative inference. Then our proposed method is further performing the several intermediate feature aggregation, namely synchronization or sync, for more active and frequent collaboration between models executed on multiple computing units. So we would like to propose an automated search method, your architecture search, and as a solution of our proposed method, which is called the SyncNAS, to search the best synchronization strategy. So this is the automated search method to maximize both accuracy and efficiency as the result of collaborative inference on the multiple available computing units on a target device. Here is the high-level overview of the SyncNAS framework. When the input, like a baseline network and target device information and latency of purpose are given, SyncNAS automatically searches and evaluates model, then pick the best candidate model. Then let's take a closer look step by step. And first, input. The SyncNAS takes a baseline network and target device information and target budget like a latency as an input. So baseline network is the network to optimize, and target device is the information of available computing units. And lastly, the budget is given a constraint like inference latency. And next, sample policy and sync case. There are several sync configurations in SyncNAS, and once we sample the combination of this configuration, we can determine the sync case. And the sync case and build model, in this stage, the SyncNAS build a candidate model by a given sync case. Then adjust the candidate model based on the profiled information. And lastly, build model and evaluation result. Based on the given candidate model, SyncNAS train the model and evaluate the model by checking the improved target accuracy. So in this section, I'm going to talk about our synchronization-aware search space. And so first, MBCon block. For the structure exploration of the model, it is important to define the search space and its criteria. So MBCon block is the structure convention inspired by Mobile Lab V2, which is widely used in lightweight CNNs. So we decide to use the MBCon block as a basic unit of our model. Then we need to determine how often we sync, where to sync, and lastly, how to sync. How often the model should be synchronized corresponds to the sync count, which is the total number of the synchronization, and where to sync corresponds to the sync position, which is the factor that determines where to synchronization between the MBCon block when the specific sync count is given. And lastly, the how to sync corresponds to the sync type, which is the factor that determines the possible sync type as, for example, element-wise sum and channel concatenation. But we have to keep in our mind that synchronization is not free. So the frequent synchronization will incur substantial runtime overhead, such as buffer allocation or memory copy. So to meet this latency budget, we have to reduce the size of the model. So naively thinking, our first expectation was that more frequent synchronization between models might extract the more sophisticated features and therefore yield a better accuracy. However, it was not true, and to check this, we choose the three most popular lightweight CNNs, Mobile Lab V2, MNASnet, and FVNet, and randomly sampled the 50 models that have different synchronization strategy while maintaining latency budget. Then, as shown in this graph, we found that our expectation was wrong and got several insights. So first, higher sync count does not always guarantee a higher accuracy. In randomly sampled in Mobile Lab V2, you can see that the most accurate configuration has sync count of 1 to 3, not a maximum sync count 7. And secondly, accuracy. It varies highly even with the same sync count depending on the sync position and types. And lastly, optimal sync strategy varies further across the baseline models. Therefore, it is hard to intuitively predict the best synchronization scenarios. So the profile guide channel estimation, we now need to reduce the amount of workload to compensate for sync cost. So in the MBCon parameterization, once the sync parameters are defined, we now have to reduce the MBCon latency to compensate this for the sync cost. So we need to define the parameter for transforming the model. So in order to estimate the sync cost and the between model, we first take a look at the MBCon block parameters. The parameter we need to pay attention is EXPC. The EXPC is the expanded channel size of output channel, and it is effective parameter to adjust the amount of workload, which is because of the total multiplier accumulate in MBCon is proportional to it. And next, MBCon and sync cost profiling. For accurate modeling of expanded channels based on latency, we measure the end-to-end latency with additional synchronization for each sync case. And secondly, expanded channel size regression. So once the sync cost is profiled and determined, the cost must be compensated by adjusting the execution of workload. So as we mentioned in the previous slide, for adjusting max, expanded channel is the effective parameter for compensating sync cost. And also by the equation below, once the required amount of max for target MBCon is given, we can determine the expanded channel based on it. And lastly, Monte Carlo tree search-based approach. So fully traversing the search space may still not be affordable due to the limited computation resource or our time. So therefore, we decide to use Monte Carlo tree search method to find an appropriate candidate model with minimal number of trials. So for more intuitive understanding, we briefly visualize our search space on figure right, so in form of the tree. So starting from the root, we traverse the tree down to the leaf node, and determine the synchronization strategy. So Monte Carlo tree search in SyncNAS consists of three phases: selection, expansion, and backpropagation. For the MCTS, we use the widely used UTC algorithm for efficient traverse and for efficient training using the multiple server. When the multiple server is available, SyncNAS sequentially sample and distribute the candidate to each server. Then lastly, we also support dynamic resource modulation. And basically, all units are not always fully available because the mobile device handles the multiple workload concurrently, and so their effective performance can vary dynamically. So in this case, we found the optimal sync configuration of full resource level that the model can be reused to build an optimized model for different resource level by fine-tuning and considering the profile information. And our framework implemented with PyTorch to support MCTS and model training, and we use also TVM, which is the deep learning compiler, for runtime analysis and parallel execution support, and optimize the model execution. For target hardware, we use the Firefly RK3399, which represents a typical modern mobile SoC. It has 2 big core of CPU and 4 little core of CPU and Mali TX60 GPU. And in model training environment, we use the multiple GPU server with NVIDIA 300, RTX 3090, and RTX A6000, etc. So as the baseline model, we choose the three widely used models on mobile platform: MobileNet V2, MNASNet, and FPNet. We also reproduce the reported validation accuracy of each models. And here is the result of our search model accuracy and latency. So in MobileNet V2, as a baseline model, we searched the model achieved the top one accuracy of 74.69% of ImageNet dataset, which is the 2.75 higher than the baseline network with similar latency. And MobileNet V2 with multiplied version, 1.2x to 8x version, 55% and 108% faster than the baseline network with this similar accuracy. And MobileNet V2 with a multiplied 1.4x version, 83% and 142% faster than the baseline network with similar latency. And the other network, like MNASNet, we found that 1.34% higher accuracy than the baseline network with similar latency. And last, in FPNet, 1.46 higher accuracy than the baseline network with similar latency. And also, in this section, the figure shows the result of our proposed model method when tightening the latency budget. So the x-axis indicates the latency budget, and the y-axis shows the top one accuracy. And as you can see in MobileNet V2, all models are higher accuracy in low latency budget. And in MNASNet, models are higher accuracy in low latency budget, except last two models. And lastly, FPNet, all models have a higher accuracy in low latency budget. So in this paper, we propose SyncNAS, a novel synchronization-aware NAS, to design collaborative models targeting heterogeneous mobile system. SyncNAS mainly focused on maximizing the accuracy by fully utilizing available resources with the given target budget. To achieve this goal, SyncNAS determined the best synchronization strategy between individual models deployed on the heterogeneous processing unit that minimize the systemic overhead while maximizing accuracy improvement. And finally, I would like to thank the Beom Kang for his most significant contribution to this work. Thank you.
Okay, thank you for this presentation. Do we have questions? Please.
So I have a question about federated learning.
Yep.
In what sense your work is different from federated learning? I mean, you consider a collaborative model for the inference, but only for the inference. So do you know any connection with the domain of federated learning or not?
Sorry, but can you say the question again?
So, are there any connection between your work and the domain of federated learning and
Federated learning?
Hmm?
Federated learning.
Yeah.
Connection between federated learning.
If you know this work, I think it's related, but I'm not sure. I'm not an expert, so.
Well, I understand what your question is. Is this work related with the federated learning, right? Well, I can't be sure about the relation between the federated learning because in this work we emphasize the transformation from the ensemble model to the more frequent synchronization between the heterogeneous the device only with the heterogeneous computing units. So, well, it's hard to in my point, it's hard to say that it's related to what you're saying. Sorry.
Okay, other questions?
You claim that you are trying to maximize the whatever hardware resources available to achieve the better accuracy as well. Yep. But one of the results actually shows that the lower latency budget, let's say the one did not really achieve the better let's say accuracy. Can you comment on that? Why?
That's accuracy. For the point that is the well, there's some kind of constraint between the several models. So I think it's really bad luck in the MNAS because there's many several reasons to transforming and yield the accuracy in the deep learning model. And I think it is the almost unpredictable to predict the total accuracy when how to transform the model. So we use the MCTS for because we don't know. So there's an assumption that we don't know how to transform the model because, of course, the explanation by AI will show the fair reason. But the assumption we don't know how to improve the deep learning model. We use the neural architecture search to improve the result, and then I guess in SyncNAS when we optimizing the MNAS-net, I think it has bad luck with this configuration, I guess.
All right.
The main reason for the question, so the main reason why we cannot achieve the better performance is that the GPU performance in the arcade, some kind of system is inferior than the CPU. So that's the thing. It is not actually helping the resource. Then switching to VR, we would like to halve the latency. So basically, we require the lower computation resources, but it is not actually. So GPU performance is inferior.
Okay. I have one short question. Have you looked at energy consumption? Doesn't that use much more energy doing that for just a little bit more accuracy?
So we can modify this formula with, so the synchronous taken input and the, sorry about that. So synchronous taken input as a based on network and target device and budget. So when the budget changed to the from the latency to the energy consumption, we can modify by the budget and change the and become and figure out how to elaborate the model by this budget. So.
Okay, there's.
So regarding SyncNAS, what was the computation budget assigned during training in hours?
Training hours. So the I can the budget is the latency. The budget we saying is the latency when the model is executed, and the question is saying that the training hour, I guess, training hours. Well, for the fast in the training hour, I guess we didn't consider with the training hour, but we also we use the MCT algorithm to fastening the training process. So yeah, we don't consider the training hours, but we also use the MCTS traverse for avoiding the duplicated searching, etc.
Go speaker one more time.